can we make this exponential number line also work for other bases? So instead of 10, let's choose a. So a step in one direction to the right means multiplication by a being some other number. And then we can repeat this and get a squared and a cubed. And also in this direction we actually divide out a. So this is 1 over a 1 over a squared, and so forth. And we get a whole continuum of values in between. First, for what numbers a does this work? You can check for yourself that it's, if you just need a scaling up, well, this means that a must be larger than 1. It can't be 1 itself, because then we would just have values of 1. And you might wonder, can we maybe use a negative value? Well, for a negative value of a, we would have sign flips from one step to the next, and then we wouldn't really be able to find or to make this work in a continuous fashion between positive and negative values. But you might want to ask, can we maybe find values between 0 and 1, so positive but less than 1, and make this work? The answer is yes, of course, but then this would be a scaling down, so the number line would actually look like this, become thinner and thinner, and just be a mirror image of these kinds of number lines that scale up. So let's stay with this. And of course, notation-wise, this would then most naturally be written a to the minus 1, like this, a to the 0, a to the minus 2. And all the things that we found out about, for example, square roots, so the midpoint, that would be still the same. Square root of a, that is a to the 1/2. And any other subdivision would give us the nth root of a, which we can write as a to the 1 over n. And so we can fill all the values in between. By limit argument, also find any irrational exponent values. So a to the pi, for example. And all this geometric intuition that we've built up, first for the exponential number line with base 10, and now with any other base, we actually boils down to the usual laws of algebra for powers. Let's write them down just for completeness. That would be, for example, a to the x times a to the y is a to the x plus y. Why? Because multiplication with a to the x actually can be represented by some arrow of some length. We can place it anywhere we want. And then multiplication with a to the y is also some length. And the rule that we've had was, if we just put one arrow next to the next to the other, we multiply with the product. With the product. And since the length on paper are proportional to x and proportional to y, putting them one next to the other means that the exponent, that is the length on paper, is actually a representative of x plus y. In the same way, dividing out a to the x is the same as multiplying with a to the negative x. So 1 over a to the x is a to the opposite x. What else do we know? Well, a to the 0, we've already settled that it's 1. And maybe also let's talk about a to the x to the power y. That is, take this arrow a to the x and then scale it up. Make copies of it if y is an integer, or just scale it appropriately on paper. So let's say, for example, by a factor of about 2.5. then this would be multiplying by with a to the x to the y, which is the same as multiplying with a to the, and now the scale length on paper, x times y. So all the rules for powers actually have a simple geometric intuition on the exponential number line, because they are the complete analogues of our basic intuitions of addition and subtraction on the regular linear number line.